I think we are live on YouTube now. So let me share my screen. Just 1 second. I don't see the screen. I have to share. Okay. So you can see my screen, hopefully. So first of all, thank you very much, everyone, for attending. And thank you, Matteo, for accepting our invitation to speak today in the Condensed Matter and Materials Physics webinar. I asked Pedro Venezuela, who was Mateo's collaborator, to introduce him. But before we introduce Matteo, let me just briefly, as usual, let me brief the next speaker of this seminar series 2 weeks from today. It's going to be Professor Axel Hoffman, and he's going to talk about topological quasiparticles, magnetic skyrmions. And today we have the pleasure to have Professor Matteo Calandra from Università di Trento, and I would like to invite Professor Pedro Venezuela from the Federal University, Fluminense Federal University, to introduce him. Pedro.
Yeah, it's a pleasure to introduce Matteo. Professor Matteo Calandra is a full professor at Università di Trento in Italy, and also he's a director de recherche at CNRS at Sorbonne in Paris. He has published more than 120 papers in international journals with more than 16,000 Web of Science citations. He works with condensed matter theory, including several topics, for instance, theoretical foundation of spectroscopy, superconductivity, quantum materials, density functional theory, electronic and vibrational properties of solids, charge density waves, graphene and 2D materials, ferroelectrics, thermoelectrics, strongly harmonic solids, etc., etc. So thank you very much for accepting the invitation, Matteo.
Thank you, Pedro. And Matteo, you can share your screen now.
Okay.
And you can go ahead.
Should see my screen now.
Yes.
Right. Okay. So first of all, thank you very much to Professor Venezuela and Professor Capaz for inviting me. It's always a pleasure to me to come here and give a talk in Brazil. Unfortunately, not physical now, but only virtually. But it's always a pleasure because the Brazilian community of science is a very nice community. I had the opportunity to experience that when I was there, and also with a very high level of physics. So it's always a pleasure to come here. So let me talk about today's talk now. Today I will tell you about the mechanism for Chandra-Density wave formation in dichalcogenides and mostly single layer dichalcogenides. So just for recognizing the importance of the work done by my co-worker. So most of the work I will tell you today was done by Yangquan Zhu, that is a Chinese postdoc that was in my group in Sorbonne Université, and by Raffaello Bianco, that is a postdoc that is now in the group of Ion and Rea in San Sebastian. And this work is done in collaboration both with the group of Ion and Rea in San Sebastian and Francesco Mauri in Roma La Sapienza. And of course, here are all my sponsors. As you know, I am at the University of Trento, but I keep one foot always in Sorbonne Université. And I am also sponsored by the Italian Institute of Technology. So let's enter in the important part of the talk, so the physics. So I started almost 10 years ago studying transition metal dichalcogenides, and in particular in bulk form at the beginning, but then more recently, due to the advent of graphene and exfoliation techniques, two-dimensional dichalcogenides. So this system, they typically display an interplay of several correlated states or structural distortion and superconductivity. Let me show you some examples. For example, this is the phase diagram of a bulk 1T titanium diselenide. And on the y-axis, you have, on the z-axis, sorry, you have temperature, and here you have copper intercalation, and while here you have pressure. I guess you see my mouse, no?
Yes,
And,
yes.
Yeah, okay. And my pointer. And so at x equal to 0, there is a charge density wave that with critical temperature approximately 200 K with a 2 by 2 by 2 structural distortion. So it means that the system, when you go below 200 degrees, it reduces the symmetry and a structural distortion take place. And when you apply pressure or like so you move here, or when you intercalate copper, the charge density wave is destroyed and leaves the place to superconductivity. The system was recently also synthesized in single layer form, or better in single tri-layer form. I will explain you later the difference. And also a charge density wave is found also in single layer. Another classical example of competition between charge density wave superconductivity is the bulk 2H iodium diselenide, where if you are at zero pressure, for example, first you have a metallic state and a charge density wave state, still metallic, that are very low pressure, a very low temperature coexist with superconductivity. Now, this system were the first system where charge density wave were actually seen to H iodium diselenide in 3 dimension or 2 dimension. And of course, in 1 dimension, the polyacetylene was the first compound. And if you look at the literature, most of the mechanisms that are assumed to be at play in charge density wave are an interplay between electron correlation and electron phonon coupling. And very little is mentioned until very last year, and particularly the work of me and my co-worker, about the crucial role of anharmonicity, namely of the fact that the potential is not harmonic, on the fact that the ion are quantum objects that can, in principle, have a wave function. However, since 2012 and 2011, we have a lot of, it's very suspicious, the fact that anharmonicity is not considered in theory, because we have evidence in experiments that anharmonicity should be important. And one of the evidence why they are important is that typically harmonic spectra are temperature independent. However, if you take, for example, bulk niobium disulfide that you see here, you can see the dots. These dots are at T2 Kelvin, and the red dots are at 300 Kelvin. And the temperature, the spectra are very, very temperature dependent. On the contrary, the harmonic approximation find imaginary phonospectra in the system, so the occurrence of charge density wave instability, while there is not in reality. And the same situation occurs in bulk titanium diselenide, where the spectra, the phonospectra in experiment are strongly dependent by temperature. So this is a fingerprint and typically of anharmonicity. That means that there is something suspicious going on, and that maybe the role of anharmonicity should be considered more in order to study this system. So for those of you that are not familiar, as far as I know, many people could connect to see the talk. For those of you who are not familiar, let me tell you what are transition metal dichalcogenides. So transition metal dichalcogenides are a system that have the stoichiometrical formula of the kind of TX2, where X is a chalcogen. So if you look back at chemistry at school, chalcogen are selenium, sulfur, and tellurium. And T is typically a transition metal. And they all form layer structures, and the bonding inside each layer. So for example, you can see here this example, the bonding inside the layer is typically covalent, but between the layer, it is a van der Waals bonding. So they are very easy to cleave. And indeed, they can, a single tri-layer, as you can see, that is usually called a single layer of niobium diselenide, can be isolated via mechanical transformation. So there is a very special way of labeling the formula, the different polytypes of the system that is typically of the community working of transition metal dichalcogenides. So this system can always exist in different polytype, And these polytype are labeled like with the following formula: lambda A Tx2. Tx2 is the stoichiometry. Lambda is a number that tells you how many layers you have per cell. So if this is a 2, for example, like 2H nitrogen diselenide that you see here, then there are 2 trilayers per cell. And A is a letter, and the letter labeled a different kind of polytype. So H, R, and T. These H, R, and T are not meaning hexagonal, rhomboidal, or something, but are simply letters. So, for example, H means that you are in that the niobium is in trigonal prismatic coordination. T, it means that it's in octahedral coordination. R means that it is in trigonal prismatic coordination, plus with a different stacking between the layers and so on. So there are many examples, for example, of dichalcogenides you can see here. And so now you have to take in to store in your mind that when I say 2H niobium diselenide, for example, or when I say 2H molybdenum disulfide, I mean 2 layers with molybdenum in trigonal prismatic coordination. And when I say 1T HFS2, for example, I say 1 layer with hafnium in octahedral coordination. Now, let me tell you that, as I told you, this system can be exfoliated, so you can you can stay with a single unit, and the single unit is a tri-layer that I will, because there is 1 layer of niobium in the plate, for example, in this case, and 2 layers of selenium. So I will call this a single layer directly for simplicity, even if it is a 3-layer actually. And the first one I would like to consider is the single tri-layer of 1P titanium diselenide, that by the language I just told you means that titanium is in octahedral coordination. The system is very interesting in single layer because, first of all, for a long time was very difficult to obtain because it is a metallic dichalcogenides, and all the dichalcogenides we will consider now are metallic because these are semi-metallic, because these are the ones that display charge density wave instability. The insulating one they do not. And for example, only very recently, due to the strong reactivity of the system, single tri-layer samples were actually obtained on different substrates. For example, HOPG, graphene, or MOS2. And you can see the sample are fairly large. And when you lower the temperature below a certain critical temperature that we call charge density wave temperature, that depends on the substrate on which you put the titanium diselenide tri-layer. I will tell you in 1 second. What happened is that a 2x2 reconstruction, of course, it's a 2x2 charge density wave that is illustrated here. And it's actually a very beautiful pattern for a charge density wave in which you can see the titanium atom are the blue one, and the central titanium stay where it is, while the selenium, 3 selenium goes close to the center, and 3 selenium moves from the center. And sorry, not selenium, titanium, I repeat. So 3 titanium, there is a fixed titanium in the center, 3 titanium move close to the center, 3 titanium move away from the center, and the selenium on top and below, they turn in such a way to minimize the Coulomb repulsion. So on the contrary, in the high temperature phase, all this titanium, they stay in exactly on the hexagon, and the selenium, they are at the position where you see the green balls. And so. Now, if you put them on different substrate, the critical temperature change. So, for example, this is the case of the bulk. Bulk titanium diselenide has a critical temperature around 200 Kelvin, slightly less, I think 197 or something like that. But then, if you put a single layer on HOPG, then the gap, this is the charge density wave gap that is measured here by STM, closes at somewhat higher temperature, around 240. And if you put it on molybdenum disulfide, closer to 108. So there are 2 puzzling things. First of all, even if the charge density wave is exactly the same, has the same pattern as in the bulk, with the only difference that in the bulk, the charge density wave is a 2x2, so it stacks along Z, but qualitatively the pattern is the same. The charge density wave temperature, and both in bulk and in single layer, there is no explanation of why the charge density wave temperature is 200 Kelvin and what are exactly the mechanism that generates the transition. There are many claims, phonon, excitonic insulators, and so on. So the single crystals of this system are so large in single layer form that it is possible to measure the atomic positions via X-ray surface X-ray diffraction. And indeed, we know that the charge density wave instability is exactly the one I showed you before. This is a somewhat more complicated plot, but it's the same that is shown before. And this has been measured also as a function of layers. For example, here you have for one TL means tri-layer, that I call single layer, and this is 5 tri-layer, 5 single layer. Now, there has been also RPS measurements, and so the RPS measurements are important because the system has an electronic structure that is not easily reproducible with the standard density functional theory method. I will show you in a moment. So if you look at the IT phase, this is the IT phase, so these two plot. So there is at the gamma point, there are 2 selenium bands that you can see sketched by the blue dots. And these 2 selenium bands are completely occupied, and they are 152 millivolts, maybe a bit less, depending on the estimate, depending on the measurement, below the Fermi level. And there is a band at N that is partially occupied, as you can see, and this is a D band of titanium. However, what happened, the point is that the system is a perfectly compensated system. So it means that if you have holes in the titanium bands here, so it means that you have hole pockets, then you must have electron pocket. But if this band is totally occupied, this band should be totally empty. However, the system does not exist in purely stoichiometric form. The system is always a bit end-doped. And this is why the reason angular resolver photoemission can see this band at the D point. If you lower the temperature, what happens is that you start see shadow bands because the endpoint and the gamma point, the endpoint fold in the gamma point because of 2x2 reconstruction, and you still see the doped band here. And there seems to be some kind of pseudo gap that open between, or gap that open between the band partially occupied and the selenium band totally occupied. And typically, the gap is 98 millivolt in the IT phase and 153 millivolt in the charge density phase. So we are talking about a system that, if we had it in perfectly stoichiometric form, would be a semiconductor with an extremely small gap. Of course, the first thing that one can try to do is to calculate for the IT phase the electronic structure. So as you can see, if you do a PB calculation, so standard density functional theory calculation with generalized gradient approximation, what happens is that the band, the selenium, the 2 selenium bands at the gamma point, they are not completely occupied, and the P and the D bands at the M point is partially occupied. So this is in disagreement with experiment. And this has been studied substantially by several workers, including me in previous works. And the same problem occurs in the bulk. So density functional theory with semi-local functional tend to overestimate the band overlap between the titanium D bands and the selenium bands. And however, this can be solved in 2 ways. So one is doing HSC06. So if you do HSC06, you obtain almost exact, almost results that are very similar to the self-consistent GW. And however, the same thing you can also do using density functional theory plus U. But if you do density functional theory plus U, you lose the charge density wave instability because the bands turns out to be correct, but not the vibrational properties. If you take the gap in HSC06 is almost perfect. The gap between the gamma endpoint is 92 millivolt against 1980. I think it's too perfect. And if you go in the charge density wave phase, at the GGA level, you have a 100 millivolt gap. And now this is plotted in the charge density wave phase, so the gap is underestimated. But if you do HSC, the gap is strongly overestimated. So it means that the gap in HSC06 turns out to be almost perfect. And also you can show, for example, that in the bulk, the structural properties are perfect with HSC06 and also the gamma phonons. But on the contrary, the electronic structure of the charge density wave, the HSC06 tends to give a much larger gap, and this is of the order of 0.3, 0.4 eV, so 300, approximately 300, 350 millivolt much larger. Now, what happened if you calculate the vibrational properties? So what we did at the beginning is to calculate the vibrational properties of the IT phase. So the IT phase at zero temperature. So of course, the IT phase at zero temperature is unstable because the system wants to distort. And if you try to calculate the phonon frequencies, you find an instability, namely you find negative phonon. So negative phonon are, for me, imaginary imaginary eigenvalues of the dynamical matrix. I plot an imaginary eigenvalue of the dynamical matrix negative, and the instability occurs at the endpoint consistent with a 2x2 reconstruction. So at the harmonic level, you have an instability, and you can see that despite the different electronic structure, the phonon dispersion is practically identical in the two functionals. So it means that the system behaves like if the electronic structure is not so important. And this is also evident if you displace the titanium atom along the pattern of the Chern wave distortion. The energy gained by the distortion is almost identical in the two functionals. So this means that in practice it's true. So, and this calculation are essentially in agreement with previous calculation 218 of Booster and co-workers. It means that the phonon dispersion, for what concern the unstable modes, not for all the modes, because you see at high temperature, at high energy, there are differences, behaves like if he doesn't know about the electronic structure and the system doesn't know about the band overlap between D and selenium. However, one can try to calculate the anharmonic correction to the spectra. This is difficult. Why is difficult? Because the anharmonicity is non-perturbative, because here you have a negative phonon, and so a very strong imaginary phonon, and the anharmonic correction is of the same order of the phonon frequency itself. So you are in the deeply anharmonic regime. And this can be done along with the techniques that we have developed in the recent year. You can see in this 3 papers. So I will not explain in details the techniques because it would take me a complete talk only for that. But it involves doing many calculations on supercell, order of 1,000 calculations on supercells with suitably chosen randomly displaced ionic coordinates. And with this, you can access directly the free energy and not only the quantum anharmonic free energy, but also the anharmonic phonon. So, of course, you have to converge on the size of the supercell. And unfortunately, however, with HSC06, we couldn't do more than 1,000 calculations on 4x4 for each temperature. I recall you the 4x4 means 48 atoms with no symmetries and K points. And so what happened is that if you include if you take PB or HSC06, you get essentially the same result for the soft mode. And what you can see is that around 80 Kelvin, the anharmonic correction push up the imaginary phonon, and the phonon become unstable if you try to fit. Here I just put the temperature at 0 and 100 Kelvin. If you fit with more temperature, you will see the instability occurs approximately at 80 Kelvin. However, it is well known that such small supercells tend to underestimate the effect of anharmonicity, but the outcome of this calculation is that even if the effect of anharmonicity is underestimated, it's practically identical in PBE and HSC06, so I can go on only with PBE that is 1 order of magnitude less expensive than HSC06. I forgot to tell you that those calculations are done with Gaussian basis sets, because of course HSC06 with plane waves on this kind of system is totally unaffordable. What happens if you do much larger supercells? So we did very large supercell up to 8x8, 10x10, and so on. And the system converges around 8x8. So 8x8 is 64 times 3 atoms. So it's a substantially a big supercell. And what happens is that the anharmonic correction is the main player. Namely, you start from a harmonic phonon dispersion that is strongly imaginary. But then when you increase the temperature, the anharmonicity push up a lot the phonons, as you can see, for different temperature, and remove the instability. However, the instability is removed around 440 Kelvin, and this is a calculation for a single layer that is suspended, so freestanding with no substrate. And the experimental one is around 200 280. Actually, this is you would think that this is a very bad agreement, but it's very difficult to achieve accuracy of the order of 200 Kelvin, because you can try to figure out how much is 200 Kelvin in EV. So 300 Kelvin is 25 millivolts. It means that your free energy must be as accurate, more accurate than 25 millivolts. But still, it's bigger than an experiment. So can we do better? And is there a discrepancy or this is an error? So one possibility is to consider the fact that the samples are doped. This is not the only possibility. So one possibility, for example, would be that the sample are strained by the substrate. However, due to X-ray diffraction, we know how much is the lattice parameter in the single layer, and the lattice parameter is exactly the same that we calculate from our calculation, and it varies not substantially between PBE and HC06. You can see in my papers all the data are given, but this function predicts almost perfectly in plain lattice parameter for the system. However, as I explained you before, the system must have a doped band here at the endpoint, because otherwise the band will not be occupied. And if you try to estimate what is the doping by comparing HC06 with different doping compensated by a positive background, you find that the system is doped approximately 4.6 10 to the 13 centimeter minus 2, which is a substantial doping. And this value of doping could be also wrong by a factor of 2, because it's very difficult to evaluate in this way the doping simply by comparing with ARPE. So if I change this one from 4.6 to 7, or probably I would still get a very good agreement with experiments. So what happens if you consider doping, so the cumulative action of doping and harmonicity? You can see here that at the harmonic level, the two spectra with no doping or with doping are practically identical. So you don't see any difference. However, if you look at the anharmonic spectra, the results are substantially different. And in particular, there is a combined effect of anharmonicity and doping. And this is due because anharmonicity, the anharmonic correction depends on the change of the phonon at all points in the Brillouin zone and on all the band, the phonon band index. So it means that any change also at high energy and everywhere affects the phonon. So small change are enough to make a different anharmonic correction in the case with the doping or without doping. And indeed, if you consider this doping, the temperature is lower at approximately 360. That is now a more favorable comparison with the 200, 280 Kelvin comparison that you have with experiment. Of course, experiments have different degrees of doping, and it's difficult to evaluate. Also, the ARPEs have different quality, but this means that we are in the ballpark anyway, and there is a combined effect of anharmonicity and doping. Now let me switch at a different compound that, however, is very similar. So up to now, we have considered 1T titanium diselenide. What happens if you replace selenium with tellurium? If you replace selenium with tellurium, the story is very funny, because in the bulk, titanium ditelluride has no charge density wave, while titanium diselenide has a charge density wave. However, when you thin titanium ditelluride to single layer, then the charge density wave emerge again, and is the same charge density wave that you see in single layer titanium diselenide. So this is very surprising, and the charge density wave temperature is much smaller. It's 92 Kelvin from ARPEs. This is not strange in the sense that the phonon spectra, of course, change when you put selenium and replace selenium with tellurium. However, what is strange is that you have an instability that comes out only when you thin the sample and not in the bottom. And you can see that the stability can be really very well seen. So we have very big pattern in the single layer. There are also diffraction. So the data, and we also see a pseudo gap, and that tells you what is the magnitude of the pseudo gap induced by the charge density wave. So everything is confirmed also nicely by STS and SCM. So what happens if you look at the electronic structure? The electronic structure is similar to the other case, but now the band overlap is more substantial and is of the same is very similar both in PBE and HSC06. However, as you can see, the velocity of the band is different in PBE and HSC06. This is true both in the monolayer and the bulk. So what happened is that even if titanium ditelluride is perfectly isoelectronic to titanium diselenite and is a perfectly compensated metal, now what happened is that it turns out that the tellurium band, due to the level alignment between titanium and tellurium, have hole pockets and are partially empty, and the selenium band on the titanium band on the contrary are more occupied. So if you look comparison with ARPE, you see the HSC06 gives almost perfect comparison with ARPE for what concern the slope of the band, the velocity, and the position of the bands. And I just recall you what was the situation in titanium diselenide, in which the bands in HSC06 there was no overlap between them. So HSC06 is good, albeit almost perfect, PBE not so. Now what happens if you calculate the harmonic phonon dispersion in these two systems? So as I told you before, when you have we take the IT phase, so the phase with no distortion, let's say. So in the bulk, the IT phase is the phase stable everywhere. In the monolayer, on the contrary, the IT phase or the phase with no distortion is unstable. And then we calculate at zero temperature its phonon dispersion. And what happens is very funny, because in PBE there is no instability neither in bulk nor in single layer. So the black phonon, they are all positive. On the contrary, if you take HSC06, the instability is present both in the bulk at the L point, so 2 by 2 by 2 instability, and in the single layer. So it means that the harmonic phonon dispersion are very different for the two cases, and in both cases they disagree qualitatively with experiment, because first of all they don't explain the disappearance of charge density wave by increasing thickness. So this made speculate. So the results that are also in qualitative agreement with another paper of Guster make the people in this paper speculating that the strain was the key mechanism to stabilize, to explain this difference. However, the point is that in order to explain this difference starting from HSC06 and you apply strain to remove the instability in the bulk and you keep it in the monolayer, you have to apply a substantial strain, which is very large. It is hardly obtainable in experiment. So another possibility would be that what is missing is anharmonicity. But before going to anharmonicity, let me tell you what does generate this kind of softening that you have seen also in titanium diselenide. So the mechanism for charge density wave at the harmonic level is the following. So at the harmonic level, the electron-phonon interaction is included in typical linear response calculation, but also finite difference. And what you calculate is a renormalized phonon frequency that is called small omega square. So this is the square of the normalized phonon frequency that is equal to a Baire phonon frequency plus a correction that is due to the electron-phonon coupling. And this correction is related to the pi prime, that is the real part of the phonon self-energy that has this shape with f that are Fermi function evaluated at epsilon kn, epsilon k plus qm. And these are the band structure. And this is the electron phonon matrix element that tells you how much, how the electronic structure reacts when you displace an atom. Now, if you, due to causality, pi prime is negative. So the correction to omega square, to capital omega square is always negative. And so the electron-phonon coupling tend to soften the phonon frequency and push it down. So the softening that you have seen that puts that leads to an instability both in bulk and single layer with HSC06 can emerge either from the matrix element or from the electronic structure. So what we know is that when we apply this normalization, the phonon frequency become imaginary, but we don't know what is the origin. Is it the electron phonon matrix element, or is it the electronic structure? You can see easily that when this pi prime has contribution, if the state Kn is occupied and the other is empty, or the other way around. So it means that when these two becomes very close to zero, you have a resonance here, and of course this diverge and tends you to give a very strong effect. So in order to understand which one of the two is important, you can, for example, assume for 1 second that the matrix element is constant, and you take it out from the sum, and you see what happens if you just consider the effect of the electronic structure, that is a so-called susceptibility, K0 without matrix element. So you can calculate this very well using Bagnier functions. So this is the so-called response function, the real part of K0, so K0 prime. And so what happened is that you have 3 Ks, so that we compare here, the bulk PB, for example, the 2 bulk PB, the mono layer PB, and here you have the same thing with HC06. As you can see, there is no qualitative difference, so both they have instability at the same point, very close to the M or L point, so the bulk is labeled. So here you have the blue is the Kz equal to pi over C. That is the one that you should see in the bulk, because the stability is actually at the L point. And in the monolayer, it's on the contrary, is at the M point. So if you want to compare the two monolayer, you have this one and this one. So you can see that with respect to the other points on the same curve, there is a softening around the point M, but the magnitude of the softening is almost identical in monolayer with PB and HC06, despite the fact that PB has practically no softening and HC06 has a big softening. So this means that the softening is actually due to the matrix element and to the fact that the exchange interaction renormalize the matrix element, so the electron-electron interaction has a strong effect on the derivative of the self-consistent potential in density function. Now, however, still, now we have explained how the harmonic calculation works, but we have still the problem that the harmonic calculation is actually finding a characteristic wave instability both in bulk and in single layer, while in experiment there is not. So what is the key, the missing ingredient? So I remember the situation at the harmonic level, a stable phonon both in bulk and in monolayer. The ingredient that is missing is actually harmonicity. As you can see, an harmonicity that of course we did only on a very small supercell 4x4 because HSC06 was too expensive. As you can see here, you can see the monolayer at 0 Kelvin that still has a slightly imaginary phonon, and the bulk at 0 Kelvin, there's no instability. So actually, the thickness dependence of the charge density wave in the system is entirely due to harmonicity. So this suggests that actually the classical theory of pair distortion due to pairs in which, due to nesting condition of the electronic structure, you have a strong energy gain by the distortion should be reconsidered, because there are two effects that are not considered. One is the electron-electron normalization of the electron phonon coupling, and the second one is the fact that an harmonicity is a huge correction and is a tremendous effect on the phonon. So let me conclude with one last example, that is the bulk and single trilayer 1H iodine disulfide, and this is a very old problem that puzzled me since 2012. When at the time harmonic calculation were at their infancy, and essentially we were not able to calculate harmonic corrections, and everything was based on harmonic correction. And apparently, if you take most of metallic dichalcogenide, bulk metallic dichalcogenide at the time, it was fairly clear that harmonic calculation, everyone was thinking, including me, that harmonic calculation were giving stability at the right points, and there seems to be no room for an harmonicity. However, as I showed you in my previous two examples, an harmonicity is very important, and also what I believe was true in 2012 turned out not to be completed. And this is dramatically true in single layer and bulk 1H iodine disulfide. So the bulk iodine, so I say 1H the bulk to say that is one layer, the single layer, sorry, 1H is one layer. So the bulk 2H nitrogen disulfide has no charge density. And this is the one I showed you at the beginning in the first slide. I will show you again soon that harmonic calculation failed completely and gives you a charge density wave. So if you take in the single layer, the situation is very puzzling because they can be grown on graphene on top of 6H silicon carbide, or they can be grown on gold 111. And in gold 111, there is no charge density wave. And if you grow it on graphene on silicon carbide, there is a charge density wave. So the situation is extremely puzzling. And the absence of charge density wave is seen in ARPES on the gold 111 also with the occurrence of a metallic band. So it's clearly out of question. And the charge density wave, on the contrary, on the 6H silicon carbide is seen very well in different experiments. In one experiment, sorry, not in different, one experiment in which STM data are shown, and this is this nano research. Now, what happened if you take the bulk, first of all? So the bulk, I calculated the bulk spectrum still long time ago, 2012, when I tried to compare with the experiment. And my calculation are actually the black dots that you can see here, and with a clear imaginary phonon at M that suggests a 2x2 charge density wave, while no charge density wave is present in the bulk. And the measurements are the blue and red dots at two different temperatures, 0 and 300 Kelvin. As you can see, from 0 to 300 Kelvin, the phonon frequency suffer more than a factor of 2 in normalization, increases by more than a factor of 2 due to temperature. And so at the time, we wrote that this would be probably due to harmonicity, but we couldn't confirm it by calculation. And now in 2019, almost 7 years later, we took again this problem and we did the full anharmonic calculation. As you can see, the temperature dependent turns out in very good agreement with the experiment for Gauss, Brillouin, and John for the low energy modes. And the instability that was found at the harmonic level is totally removed by harmonicity. So harmonicity stabilized the lattice in bulk nitrogen disulfides. Now, what happened in single layer? In single layer, if you use experimental lattice parameter, so what happened is that the system is much closer to a 0 Kelvin, even including an harmonicity, to a charge density wave instability. You see the phonon frequency is very, very small, 2 or 3 millivolts after harmonicity. On the contrary, at the harmonic level is very imaginary, and the periodicity is different because the periodicity is about 0.72. The Q is about 0.72 gamma M that is compatible, is very close to a 3x3 that is actually seen in the bulk. So what does it mean? It means that this result is extremely sensitive to strain and external perturbation, and small external perturbation could in principle completely change the situation. So it means that it's very clear that depending on which substrate or on which doping or whatever you have, you can easily fall in a charge density wave or go away, because this value of the frequency of 0 Kelvin is really, really small. So for example, if you just expand the parameter by 0.5%, you get a perfect 3x3 charge density wave, confirmed even at the anharmonic level, which tells you again more about the sensitivity of the system to external conditions. So let me conclude. So I told you practically everything I wanted to tell you. So there is one important point that has to be considered, and the important point is that anharmonicity, is crucial in the theory of charge density wave, and the old theory of pair in which simply you can consider the energy gain by the distortion as due to the band gap opening is completely incorrect in these systems, because you have always the interplay between 3 different effects: the electron-phonon interaction, the effect of the electron-electron interaction on the electron-phonon coupling, and most importantly, the anharmonic effect. So in a single layer titanium dicyanide, there is also an additional effect at the point that the samples are actually slightly electron doped, and this makes you this quantitatively explain the occurrence of the charge density wave. So there is a combined effect of phonon anharmonicity doping and electron-phonon interaction. And the system has been single layer 1T titanium diselenite, and Wagner have always proposed as possible excitonic insulator. Actually, there is no need of considering excitonic insulator to explain the occurrence of charge density wave. In titanium ditelluride, as I told you, the explanation of the thickness dependence of the charge density wave is entirely due to tonicity, because at the harmonic level, you either do not explain the occurrence of the instability both in bulk and single layer, or you get instability in both. And finally, 1H nitrogen disulfide, a very long, 7-year long standing problem in which there was a totally disagreement between theory and experiment, can be explained with excellent agreement if an harmonicity is included. So all this point out to this crucial role of going beyond the harmonic calculation. And actually, I would like just to advertise very quickly that we are releasing probably in 1 week or 2 weeks the code for an harmonic calculation that requires simply the use of an external force engine that could be density functional theory force engine, but could also be simply empirical potential, anharmonic empirical potential force engine, and so on, any force engine, and it will be available for free and will be distributed. So with this, I conclude, and I leave the word to. I stop sharing, I guess, and I don't know if I have to continue sharing.
You can keep sharing,
okay,
Matteo.
okay,
yeah.
Okay, so, and I leave and open for questions.
Thank you very much, Matteo. As usual, people can ask questions by raising your hand at the Zoom app, or you can write your question here at the chat, or you can ask questions at the YouTube transmission. I can start with a general question, Matteo. You mentioned in the beginning that charge density waves could also be driven by electronic correlations, but apparently, at least for the systems that you're considering, apparently they are not playing an important role, or at least they are not needed to explain
So in these systems, the system are probably not enough correlated to have charge density wave driven only by electron-electron interaction, as it might happen in cuprates or also in one-dimensional materials like carbide and so on. So anyway, my feeling is that even in a system where the charge density wave is driven by an electronic mechanism, namely there is the possibility of stabilizing a distorted ground state only keeping the atom frozen but leaving the electron moving. My feeling is that even in this case, probably if you relax completely the atomic position and optimize, you will see that the greatest energy gain is given by the lattice energy gain. So one question is, what is the mechanism that starts the charge density wave? This is difficult to answer in many cases because it's not so clear. Sometimes you cannot completely disentangle the degrees of freedom. But what is probably true is that in most of the cases, the most of the energy gain is given by the lattice relaxation.
I see. Good. So, is there any other question? I have actually another question related to precisely to this slide you are showing. It seems that for 300 and 400K, I mean, the imaginary part of the relevant phonon mode at M is about the same, right? Is there any reason why? I mean, it's just a curiosity.
Well, what happened is, I understand. No, please go ahead. Sorry, I stopped you.
No, yeah. Is there any meaning for that?
No. So what happened is that we are looking at the charge density wave from the top, the transition from the top. So we are looking at the temperature larger from the charge density wave transition, and we are looking how the mode becomes soft. So in this case, above the charge density wave transition, omega squared goes linearly, omega squared. So omega goes essentially as square root of T minus Tc. However, below, this is not given. And indeed, what we find is that there is the behavior below of the phonon, which is imaginary, because actually what happened at this point is that what should happen is that at this point that you release the lattice, and the lattice becomes change shape, and so the phonon frequency changes completely. What we are looking at when we look at the imaginary frequency is the atomic positions that are fixed and the phonon that is however unstable. So what happens is that the temperature dependent in this case change below such an ST wave temperature and becomes much weaker. And there is actually nothing that tells you that this temperature dependence should still be linear below when the phonon has already become imaginary. This is why. Generally, what we see is that there is a small region of temperature where this is all constant, and then it decreases a bit more.
Great, thank you. So there is a question from Eduardo Miranda. Eduardo, you can ask your question.
Okay, thank you, Matteo, for a great talk.
Thank you.
Perhaps you can say a few words about superconductivity in these systems.
Yeah, yeah, of course.
From the phase diagram, it looks like it's always at the point where the charge density wave goes to zero or disappears.
Not always. It depends strongly on the system. So this is a very good question indeed. So one case is the case of titanium diselenide. So for example, this is the bulk. Now, first of all, I would like to tell you that in single layer form, there are several reports of superconductivity. Not in titanium diselenide, but for example in iodine diselenide, but TC is not uniform between different reports, changes substantially. So probably single layer are very dependent on environmental conditions like the effects and so on for what concerns the superconducting TC. On the contrary, if you look at the bulk, whether this is a very well established case, so to H iodine diselenide. Here, for example, you see that superconductivity is almost constant TC if you are deeply inside the charge density wave or if you are outside. On the contrary, here, the situation is different because at the emergence, so when charge density wave emerge here, then superconductivity has some kind of DOM feature. Actually, these two facts can be traced to completely different behavior of phonon. So in this case on the right, what happens is that charge density wave phonon is determined by the low energy phonon, but superconductivity is phonon mediated is due to high energy phonon. So the high energy phonons, they don't feel too much the fact that you have a charge density wave instability. And the superconductivity has almost constant critical temperature, slightly increasing with pressure. On the contrary, here the situation is that superconductivity is mediated by the low energy modes, phonon modes that are the same that induce the charge density wave instability, and so there is a very strong dependence on the emergence of charge density wave instability and superconductivity. So this is why in the system there is this difference. Then there are many cases in which, for example, the case if you replace 2H iodine diselenide with disulfide, so you remove sulfur, you don't have the charge density wave instability, but you still have superconductivity practically at the same critical temperature. It seems that in this system, for example, here, iodine diselenide and disulfide, the coexistence between the two is almost accidental. So you can have the same superconductivity in the isovalent compound with sulfur without having charge density waves. So they live in two separate worlds because they are mediated by completely different phonons. On the contrary, here the situation is not the same. Either you have charge density wave or you have superconductivity because they are mediated by the same phonon. Okay. So in all dichalcogenides, in most dichalcogenides, there is this twofold possibility. So in some case, there is an interplay between the two because the phonon are the same, and in some case there is the two phenomena lives separate.
Thank you.
You're welcome.
Thank you, Eduardo. There's another question from Nathanael Costa. Nathanael, you can ask your question.
Yes.
We can't hear you, Nathanael.
Yeah, I don't hear. Yeah.
I believe now you hear me.
Yes, yes.
Yes.
It's just a simple question. You focus your your presentation on the harmonicity effect. But we know that, for instance, in the 1T structure, we have flat bands. So in flat bands, you cannot disregard electron-electron interactions. So can you give some comments about this, about the role of
so it depends of the 1T, it depends of the 1T polytype. So for example, just let me show you again one thing. So here in this 1T polytype, here, for example, you don't have really flat bands. You see, so yeah. Nevertheless, electron-electron interaction is important because when you do an HC06 calculation, it means that you have included a screened exchange interaction in the calculation. Now there are more exotic kind of dichalcogenides. So for example, not more exotic, there are other dichalcogenides. So let me show you. So for example, the classical example is 1T tantalum disulfide, in which there is a very flat band. In this case, probably, so I didn't do this calculation, but in this case, most likely, the electron-electron interaction is very important. So another case where it is very important, let me show you because I have it here, and it's very similar to the case of tantalum disulfides, is this 1T niobium diselenide that was synthesized very recently. And in the system, indeed, there is, so I will not tell you the full story, but this system are very analogous of tantalum disulfide because they do a square root of 13 reconstruction. And just to tell you, when you have this square root of 13 reconstruction, that is a Star of David, you probably know very well. So what happened is that the number, so you always have a situation like this in which the electronic structure of the undistorted structure, for example, has one electron in the dz minus r squared orbital, and when you have the square root of 13 times square root of 13, you have an unpaired electron that is left because you have 13 atoms. And so if this is an insulator, it cannot be a band insulator because you have an impaired electron unless it is magnetic. Now, for example, in the case of tantalum disulfide and niobium 1T diselenide, but more in tantalum disulfide, there were a lot of questions if this is a multi-insulator, if it is not a multi-insulator. Most important person considering it a multi-insulator was Erio Tosatti, probably. And this is very difficult. So I just have also one slide somewhere to show you, but I cannot find it at the moment. So okay, I will just tell you with my words. So what happened is that this was contradicted, and actually not really contradicted, in the sense that there were other proposals. So in the sense that there is surely a flat band, the electronic interaction are important, more important in the case I showed you. However, recently it was shown that the stacking that was considered the one of tantalum disulfide is probably not the stacking that was considered in that was measured many years ago. And then there were other papers showing that ARPES was showing a metallic phase, so it's not even more clear if the tantalum disulfide is still a multi-insulator or not at the moment. But surely you have some of these 1T, and I agree completely with you, in which you have very flat bands. And in this case, of course, the situation is much more delicate than the case that I show you, where you don't have a really flat band, and the correlation effect are more important. However, I would like to recall you that even in this case, if you do test the functionality calculation not with semi-local function, but with more advanced function, you always qualitatively explain the occurrence of the charge density wave. What you don't explain are the details, the magnitude of the critical the charge density wave temperature. You maybe do not explain completely the velocity of the Fermi velocity and blah blah and so on, and or the velocity of the band and so on. But you qualitatively and semi-quantitatively explain the occurrence of charge density wave. But I agree with you that the system are more delicate, particularly those that does a David star reconstruction with square root of 13 square root of 13.
Okay, thank you very much.
Thank you. We have another question now from Fernando.
Yes, Fernando.
Fernando, you can ask your question.
Hi, I'd like to thank first for the very nice talk.
Thank you.
I'm quite new to the field, so I have some very basic questions, right?
Yeah.
First, what I see is that you are calculating this phonon spectrum,
Yeah.
and then you see the softening, which
Yeah.
I think is kind of a cone anomaly, if I'm not mistaken.
Yeah, exactly.
Okay, so from that you convert that in the Chardon's wave transitional temperature. So I believe there is a theory behind that. So I don't know
Yeah.
if you can elaborate a little bit to me. So
Yeah, so essentially you have two ways in which you can look at the occurrence of Chardon's wave transition. One is that you look at the gain of free energy between the low T phase and the high T phase. And this in general, you can, if you have a first order transition, you just look at the difference between the free energy of the high T phase and the low T phase. If you have a second order transition, you can also look at the difference in the phonon, you can also look at the high T phase and see when at which temperature the phonon becomes imaginary. Why? Because maybe you can think in terms of Landau theory. So if you have Landau theory, so when you have an instability, then your potential starts developing a double minimum. And if you are on the top of the minimum, so you are, if you are on the maximum and not on the double minimum, then the second derivative of the free energy, or at zero temperature total energy, but a final temperature of the free energy, then is negative. If the second derivative of the free energy is negative, you can show that the second derivative of the free energy is related to the phonon frequency at final temperature. Okay? And so this tells you why, when you start developing in Landau theory a second order transition, then your phonon, if you look from the above, must become imaginary. So this is not, is similar to an anomaly, and namely, it's a anomaly at the harmonic level. But when you include an harmonicity, it's not anymore an anomaly, because you have also the harmonic correction. And then you can only talk in terms of Landau theory and of the free energy, because you have the free energy, the quantum and harmonic free energy. So the theory beyond then is the cumulative effect of the core anomaly plus Landau theory of phase transition, of second order phase transition.
I see. But for instance, since you're not including electron-electron correlations, I would say that something like you have an electron system and electron phonon coupling, right?
No, we have also the electron-electron interaction, because
and also
we have the exchange and correlation functional. So when we use a semi-local functional, we have what is called the local density approximation and so on. But when we use a more complicated approximation to the electron-electron problem, like HSC06 and so on, you have also Hartree-Fock screened exchange. And so you have electron-electron interaction, mostly the Hartree-Fock term, and only locally the correlation part. But you have the electron-electron interaction. So, and not only you have it in the electronic band structure, but you have also in the force constant. So the force constant are derivative of total energy, are derivative of total energy that includes the electron-electron interaction. Okay.
Okay, but I mean, what you're telling me is very similar to, like, say, a BCS theory that, leads to a superconductor. So what actually, changes here? I mean, at a harmonic level, right? I mean, what at a harmonic level? I'm not talking about the anharmonicities, which I think it's much more complicated. But
no, at the harmonic level, the situation is similar to a quantum anomaly.
I see.
But there is one difference, in that the idea of the common anomaly is that, let me just go quickly to the slide. Yeah. The idea of the common anomaly is that everything is driven by this denominator that becomes small. However, this is not the case here. The denominator is not becoming smaller. What drives the transition is the matrix element. So the matrix element is how the Hamiltonian felt by the electron change when you displace an atom. Okay? So the K and Q dependence of this matrix element and the dependence of the matrix element of the electron-electron interaction is what gives you more softening than the standard anomaly theory. So if you want, this is the standard anomaly theory with no matrix element, and this is a bit more complicated anomaly theory at the harmonic level. So you need this, and indeed, depending on the approximation of the electron-electron interaction, the G change. So it means that different degrees of electron-electron interaction renormalize differently the electron phonon matrix element.
I see.
Is it clear?
Yes, yes. I mean, yes, I think so. I think a little bit, but yes, I see. Okay.
Thank you, Fernando.
I mean, I would
okay.
like to have one more very general
Yeah.
question. I mean,
Yeah.
why? I mean, how can I understand? I mean, at least from your talk, I could see that most of the anharmonic effects will actually be relevant for, you know, single layers, a single tri-layer materials, not for bulk materials.
No, they are also important for bulk materials. The point is that the point is that calculations are much heavier for bulk materials.
Ah, I see.
But we have in this talk I mostly focus on 2D materials. But if you look at my publication, for example, I also calculate for other materials. So I did the most of dichalcogenides, both in single layer form and in bulk form. So in bulk form, in most of the case, we are less accurate to charge density wave transition, but we are also still fairly accurate. And the reason why we are less accurate is that the calculation is more expensive. But every time you have a second order phase transition, anharmonicity is very important.
Okay.
Because what means a second order phase transition? Means that you have second order phase transition in which the lattice becomes soft. Okay? If the lattice becomes soft, so you have a soft mode, then it means that your second derivative of the energy is very small. And so it means that your potential is extremely flat. And if the potential is very flat, the anharmonic correction between become important. So it means that the second derivative is almost zero, then the third derivative becomes important, not third and fourth derivative. So every time you have a second order transition implying the lattice, anharmonicity plays an important role. The magnitude of this role, of course, is more difficult to evaluate, but you can expect that it plays an important role.
Okay, thank you. Really
You're welcome.
Thank you, Fernando. Is there any other questions? I don't see any other questions here. So if not, I would like to ask all the audience to open their microphones, and let's give a hand of applause to Professor Matteo Calandra. Thank you again, Matteo, for accepting our invitation.
Thank you very much. It was a very pleasant talk with extremely good questions, and it's a pleasure when you have so good questions to reply to.
Thank you very much. I will now stop transmitting the YouTube. Just 1 second. Okay.